Hey everyone, welcome back to my YouTube channel, Our Solar System. For centuries, we gazed upon its familiar planets, believing we understood its fundamental architecture. A fiery sun, rocky inner worlds, gas giants in the middle, and then the icy, desolate fringes. A neat, predictable cosmic neighborhood. But beneath this comforting veneer of understanding, a profound secret has been slowly, painstakingly unveiled. It's a secret that challenges our most basic assumptions about where life can thrive, transforming our perception of our own backyard from a collection of dead rocks and gas into a vibrant, dynamic realm teeming with hidden possibilities. You're talking about the solar system's secret worlds, vast, liquid oceans tucked away beneath miles of ice, far from the life-giving warmth of the sun. These aren't mere puddles. They are oceans potentially larger and deeper than any on Earth, shrouded in perpetual darkness, yet potentially brimming with life. This is the ultimate cosmic mystery playing out right here, within our reach. For generations, the search for extraterrestrial life focused almost exclusively on Mars, a dusty, red world that once held liquid water on its surface. He envisioned life requiring sunlight, a temperate atmosphere, and liquid water freely flowing. But the cosmos, as it often does, had a more imaginative story to tell. The anomaly we now confront is the realization that some of the most promising abodes for life in our solar system are not sun-drenched surfaces, but rather the deep, dark interiors of distant, icy moons. Worlds like Europa, orbiting Jupiter, and Enceladus, a tiny satellite of Saturn, have emerged from the shadows as prime candidates in the quest for life beyond Earth. They possess the three critical ingredients: liquid water, energy, and organic molecules. But how can liquid water persist in such frigid environments, hundreds of millions of miles from the sun's comforting embrace? What kind of energy could sustain these hidden oceans, and perhaps the life within them? This is the core astronomical mystery we seek to unravel. The implications are staggering, suggesting that life might be far more common in the universe than we ever dared to imagine, flourishing in places we once dismissed as utterly hostile. Act 2. The first clues, the first whispers of these hidden worlds, came not from sophisticated probes, but from the keen eyes of early astronomers. Galileo Galilei in 1610 turned his crude telescope towards Jupiter and discovered its four largest moons: Io, Europa, Ganymede, and Callisto. These Galilean moons were, for centuries, little more than points of light, their true nature utterly unknown. It wasn't until the dawn of the space age, with the Voyager missions of the late 1970s, that their individual personalities began to emerge. Voyager 1 and Voyager 2, on their grand tour of the outer solar system, provided humanity's first close-up glimpses of these distant worlds. When Voyager 1 and 2 flew past Jupiter in 1979, Europa immediately stood out. Unlike its heavily cratered siblings, Europa's surface was remarkably smooth, almost pristine, with a striking network of dark, reddish-brown lines crisscrossing its icy shell. It looked like a cracked eggshell, or perhaps a shattered pane of glass that had somehow refrozen. This smooth, fractured appearance hinted at geological activity, but what kind? Scientists began to theorize. Could the interior be warm enough to melt ice? The dominant theory that emerged was tidal heating. Jupiter, being the most massive planet in our solar system, exerts immense gravitational forces on its moons. As Europa orbits Jupiter, the gravitational pull varies, constantly stretching and squeezing the moon. This internal friction, much like repeatedly bending a paperclip, generates heat. It was proposed that this tidal heating could keep a layer of water liquid beneath Europa's icy crust. But this was still largely speculation, a tantalizing hypothesis based on visual clues. The true revolution in our understanding of Europa came with the Galileo mission. Launched in 1989 and arriving at Jupiter in 1995, Galileo spent 8 years orbiting the gas giant, making multiple close flybys of its moons. Galileo's magnetometer detected a distinctive induced magnetic field around Europa. This was a critical piece of evidence. A magnetic field induced by Jupiter's own powerful magnetosphere strongly suggested the presence of a vast, electrically conductive layer beneath Europa's surface. And what is the most plausible electrically conductive liquid in an icy moon? Saltwater. The evidence was compelling. Europa almost certainly harbored a global, salty ocean beneath its icy shell, perhaps 100 kilometers deep, containing more water than all of Earth's oceans combined. The initial clues were coalescing into a coherent picture of a hidden ocean world. Meanwhile, another icy moon, far out in the Saturnian system, was beginning to reveal its own secrets. Enceladus, a tiny moon barely 500 kilometers across, had also been visited by the Voyager probes. They showed it to be a bright, icy world, but nothing particularly extraordinary. It was the Cassini mission, launched in 1997 and arriving at Saturn in 2004, that completely transformed our perception of Enceladus. Cassini's instruments provided an unprecedented view of Saturn and its complex moon system. During a close flyby in 2005, Cassini detected plumes of water vapor and ice particles erupting from the moon's south polar region. spewing hundreds of kilograms of material into space every second. These plumes, dubbed the tiger stripes due to the distinctive fissures from which they emanated, were an undeniable sign of active geology and, crucially, liquid water. The discovery of the plumes was a game-changer. It wasn't just inferred, it was directly observed. The plumes were composed primarily of water vapor, but also contained salts, organic molecules, and even tiny silica particles. The presence of silica nanoparticles was particularly exciting, as they are typically formed when hot water interacts with rock, hinting at hydrothermal activity.